Okay, welcome to EGR445 Mechanical Engineering Systems. In this class, we are going to study different types of mechanical systems, and we are going to use the material that you studied in EGR444. The lectures will be video recorded, and I would upload these lectures on YouTube in 4K. So you can watch these lectures later if you want to in high definition. Also, the captions are also provided. So that way, if there is any discontinuity or you need some discussion, or if you need to go back to what I said, you have that option. So I'm going to go through the syllabus in today's class, and we will go through the Canvas website. I will talk about all the information out there, then give you some pointers on how to study, and then we will study the basic concepts and review and work out a few problems. Now, the syllabus is uploaded on Canvas. So take a moment to review the syllabus. My name is Sangram Redkar, and my email is sredkar@asu.edu. I have given my contact information. My office hours are by appointment. So if you want to make an appointment, just shoot me an email, or I would be happy to help after the class. The course description is given as different electromechanical systems, electronics, hardware, software development, and we will try to incorporate these concepts in an engineering subsystem. And the subsystem that we will study is internal combustion engine. 3 credits. The class will be on Wednesdays, 6 to 8:45. It's a long class. So the way we would do this class is I will teach from 6 to about 7:15. At 7:15, I will give you a break for 15 to 20 minutes. Then we will come back and then discuss and work out the problems. Again, this is once a week class, and it's going to be a lot of information coming to you. We will work out quite a few problems, and this would be a fun class. So I just want to let you know that this course is dependent on EGR444, and most of you have done very well in EGR444, and we would study the similar concepts, but we will apply them in the case of design and development of mechanical system. The book that we are going to use is Textbook of Machine Design by Khurmi Gupta, and we will talk about selecting different components, analyzing different components, studying them at subsystem level, and then studying these concepts at system level. And the student learning objectives are, we should be able to apply design principles that we studied, try to be able to solve practical problems, use software to solve design problems, and then look at the industry standards on how to select components, how to put the components together, and so on. So how to succeed in this class? So even though attendance is not required, I would strongly recommend all of you to attend the class, because this is a time where you can work with me. I will be solving problems step by step, and then work out the problems with me. And then if you have any questions, you can ask them. Feel free to stop me anytime if you don't understand the material and ask me any questions you may have. I would be uploading some material. So specifically at the end of every class, I will upload the PowerPoint slides for that class in the Canvas. You can use those as reference, and you can watch the video lectures. I would provide the link to the video lectures on Canvas website, and I will also create a YouTube playlist. That way you will have all the material or the course information at one location, and you can review the material at your own pace. Now, the grading standards. So 90 and above is A, 80 and above is B, 70 and above C, 60 and above D. I just want to be clear and make it explicit that the quizzes will be 60% of the total grade. Quizzes will be 60% of the total grade, and homework will be 40% of the total grade. And that breakup or breakdown is shown in the Canvas. All the assignments will be submitted via Canvas electronically, and please don't submit assignments via email. Late or missed assignments, unless you have a valid excuse, late submission will not be accepted. So please don't turn in late assignments. And if you need extra time and if you have valid excuse, then please contact me in advance and let me know the accommodations you need. I understand these are uncertain times, and sometimes there could be reasons beyond your control, and we will try to accommodate all that as per the university policy. Then be aware of drop and add deadlines, withdrawal dates. There is a process for a grade appeal, and please make yourself familiar with the grade appeal process. At the end of the course, please do the course evaluation. That is very helpful. Now, the syllabus here is sort of tentative, and it's quite possible that based on how the class progresses, there could be some changes. but these changes will be announced well in advance. Now, I know most of you are taking 3-4 classes. Some of you are working. Some of you have families and taking care of small kids. So I just want to give you the overall schedule for the entire semester in advance, including the homeworks and quizzes and their due dates. That way you can manage your time effectively. So if you look at the overall schedule, we have about 15 classes. And the first class, today's class, on 113, we will talk about basic introduction. We will cover the chapters 4 and 5 from the textbook. And these chapters you must have studied in mechanics of material and engineering design. So we will review those concepts related to stress, strain, different types of stresses, and then torsion, the effect of combined bending and torsion, principal stresses, etc. And then homework 1 is already assigned. If you go to Canvas, the homework is already posted. Next class, we will look at a mechanical system that is called as the cotter joint. Cotter joint is used to connect two rods. Then we'll move on to knuckle joint. Knuckle joints is sort of a hinge. It's also used to connect two rods. Then we will look at design of shaft, keys, and couplings. We will move on to design of turnbuckle, design of screw jack. Then we will look at design of springs, design of spur gear. Yeah, I would talk about the formatting requirement in just a second. Design of spur gears, design of helical gears, design of bevel gears, design of worm gear, and the last 3 to 4 lessons will be devoted to design of internal combustion engine. So what I would like to do is I would like to teach you how to design a single cylinder internal combustion engine. Because if you look at the internal combustion engine, it's a very complex system that comprises of electromechanical components. So once we study the springs, spur gears, rods, cotter joints, all these subcomponents, internal combustion engine is the complete system where all these subcomponents, mechanical subcomponents, come together. Then we will review. I just want to mention here is I have listed these topics as a guideline. But so these are the bare minimum topics that we will be covering in this course. But I just want to tell you that when you graduate from this program, and most of you are seniors, when you graduate from this program, you will be entering industry, and the information that you will learn in this class is very important from industrial point of view. I mean, I want you to know the difference between the helical gear, spur gear, where are those different gears used, what are the advantages, disadvantages, What are the different type of couplings? What are different types of joining methods? Which one would you use? When do you use bevel gear? How does an internal combustion engine actually work? What are the different mechanical components in the internal combustion engine? And some of you are taking this course are from automotive concentration. So you probably have seen the engines. And in this class, we will talk about how to design piston, cylinder, uh, cooling system, connecting rod, crankshaft, camshaft. Uh, you must have studied about two-stroke engines, four-stroke engines. What are the differences? How do the designs differ? And then you will get some practical understanding of why particular engine is designed that way. And some of you must be working on cars. If you are a car nut like me, then probably you like working on your cars, opening up engines, fixing them, uh, tuning the engines. So this course will give you some engineering background on how to do some of these practical things. But I would anticipate that we will be able to cover a lot more material than the bare minimum material that is discussed above. So that is the material we will cover for sure. But usually what I do is I cover a lot more than the required material. So, but these are at this point, I would like to post them as optional topics. So I would like to discuss design of clutches. So for an example, if you drive a stick shift, you have a clutch mechanism. That way you can change the gear. You use the clutch to separate the engine from the transmission, and then change the gears, change the power, change the torque and speed characteristics. So clutches are an integral part of a power transmission device, power transmission system. Then brakes, you have internal expanding brakes typically used in automotive, or you have external drum brakes that are typically used in bikes or some prime movers. So why do we use brakes? Where are they used? For an example, if you're driving slightly older cars, you will see that the drum brakes are on the rear wheels and the disc brakes are on the front wheels. So why is it designed like that? So what are the advantages, disadvantages? So we will talk about brake design. Then we will talk about the flywheel design. Flywheel is sort of a mechanical capacitor. What it does, it takes the energy from the power stroke and supplies energy to suction, compression, and exhaust stroke of internal combustion engine. So it actually helps to smoothen the torque requirement. So we will talk about the flywheel design. We will talk about flat belt and pulley design. And belt and pulley design, if you see the serpentine belts in your cars that drive the fan, the the compressor, air conditioning compressor, alternator, power steering pump, they have belts. They could have flat belts in the older designs. nowadays they have V belts. A step further is using a toothed belt, and the timing belt is basically a V belt with teeth. Then we will talk about the bearings. So there are two main types of bearings. One is the sliding contact bearing, and other one is the rolling contact bearing. These two different types of bearings are used in internal combustion engines. They are used in power transmission devices. So we will use these subsystems in lot of mechanical engineering applications. So this course is very practical. So some of these systems you might have seen throughout your engineering curriculum, or if you are working, you might have seen these in industry. And we will talk about how to design different types of systems. Now, please make yourself familiar with the university's policies for the classroom behavior, academic integrity. The expectation is that you will work alone on the quizzes, but you may form study groups for homeworks. So it's totally fine to help each other, but at the end, you should take pride in your work and you should turn in your own work and spend time in studying the material. And plagiarism, so please don't copy either from online or from your friends. Just use your own work and make yourself familiar with the threatening behavior, harassment and sexual discrimination policies, and disability resources that are given in this syllabus document. This course is going to use ASU Sync. What it means is I will be live teaching, but the course will be recorded. And you are welcome to interact, raise your hand, or use chat to ask questions. Now, at this point, I want to ask you if there are any questions pertaining to syllabus. So the first question is exams. Yes, there are exams. In a sense, there are quizzes, not exams. There is no final exams. All quizzes and homework are take home, open book, open notes, and you will upload the solution to the homeworks and quizzes on Canvas. Something I need to clarify on the homeworks and quizzes. Some of these homeworks and quizzes expect you to use SolidWorks because we need to know how to use computer software as part of this learning objective to design mechanical systems. So most of you have taken SolidWorks. So you will use SolidWorks or Autodesk Fusion for design. And I totally understand that SolidWorks only works on Windows. So there are two options. Either you can use Citrix and remote login to ASU network and use SolidWorks on ASU network, or you can use SolidWorks in the library and other ASU facilities on the campus. If that is not possible, then Autodesk Fusion is also equally good software. It's available free of cost to students with EDU email ID that you can use to download. And again, ASU as I understand, you can rent computer, as Cole rightly said. You can try that, or you are welcome to use Autodesk Fusion, because Autodesk Fusion works on Mac, and it's equally good, and it is very simple to use. The next question is if there are any specific formatting requirements. Now, I recommend you to use engineering paper, because engineering paper is uh, it's a graph paper on one side. So if you want to draw figures, you can actually use that graph paper. And alternatively, some of you might use Surface or iPad. You can actually uh, have a graph paper on iPad or Surface and do your assignments and homeworks there. Alternatively, if you are using iPad and Apple Pencil, the way I do it, then it's also very easy. Okay, are there any other questions related to the syllabus? But at the end, you please turn in only one PDF with the homework and the quiz. Please don't take snapshots and then upload those as JPEGs. So please turn in just one PDF. And one thing that you can do is, if you are using engineering paper, if you work out the problems on engineering paper, scanning is free at all ASU facilities. So you can go to library and scan, convert that entire document into one PDF, email it to yourself, and upload it onto Canvas. Alternatively, if you are using app, there are scanning programs or scanning apps that you can use, but don't upload individual scans. Just combine those, make it into one PDF, and then upload. The grader for this class is Mr. Asjad Malik, and he has logged on. So what I'm going to do is, Asjad, I'm going to unmute you for a second so you can introduce yourself, and then type in your email ID in the chat window.
Hi, I'm Arshad. So I am a master's student in mechanical engineering, and I have some industry experience as a design engineer. And this is my third semester that I'm assisting Professor Redkar with courses. I worked as a grader before for this course in the spring 20 semester, and let me tell you that this is a very interesting course. And as Dr. Redkar said, this will train you in essential skills like 3D modeling, simulation, failure analysis, and many more. One thing like I would really like to share about this course is that to get good grades, I would say what I would do is that I would submit all of the assignments and not miss any of those, because missing any of those assignments would cost you one letter grade. So yeah, that's what I would do. Uh, and yes, if you have any questions regarding the grading, you can email me directly at eamalik3@asu.edu. I would share this email address in the chat box, and mostly I would also send an welcome email regarding the details. And yeah, that's pretty much it. So good luck everyone with this course, and thank you, Professor Redka.
All right, thanks, Asjad. Now, what I'm going to do is, I'm going to, are there any questions for Asjad? If you need to talk to him or meet with him, he is available via email. So you can send him an email and I'm sure he can set up a time and either meet you in person or via Zoom. So now let me switch to Canvas and show you what information is available on Canvas and how to use it. So I'm gonna share the Canvas screen. So you should be able to see my Canvas screen. Now, if you go to the screen, please note that assignments are already posted. So quiz 1, quiz 2, quiz 3, quiz 4, quiz 5 are already uploaded. So if you click on quiz, you can open the quiz 1 docx, and then it also shows you when this quiz is due. Typically, you will have about 2 weeks to finish quizzes, but you may have about 1 week to complete the homework. Now, homeworks are also posted, so I would strongly recommend that make yourself familiar with all the homeworks. What are they expecting? Because I would expect homework to take anywhere between 2 to 3 hours. Quizzes would also take about 5 to 6 hours. So I would anticipate. So just if you go to quiz here, and what you do is you will see a file upload. So this is where you should submit or you should upload. Go to assignments, and then you should be able to upload the homework and the quizzes. You should see a link. That link is not visible because this is the instructor view, but quiz 1 upload should be available in your view. Yeah, let me just a second. Yeah, Jonathan, you are unmuted.
Yeah, when are these quizzes initially unlocked? And essentially, like, is it going to be just for that class day, or do we have the week to work on it?
Okay, so typically, if you look at the schedule, uh, on the syllabus, we have posted the day the quizzes are assigned and homeworks are assigned, and the days when the quizzes and homeworks are due. For example, homework number 1 is assigned today. That is due.
Is actually, just not to cut you off or anything, is there a separate syllabus? Because the one that I'm pulled up on your that's the on the landing page for the syllabus doesn't have the actual schedule with it.
Oh, okay. Then I don't know what the mix-up is. I will. So this syllabus. Okay. Let me see. So the skid. Okay, I will check what's going on. But the schedule that we discussed in today's class, uh, that is what we will follow. But I will check. I don't know what the mix-up is, but I can upload or update the syllabus. And if you like, I can email that to all the students as well.
Okay, thank you.
But if you look at the dates, these are the due dates, and all these homeworks and quizzes are unlocked. So which means if you want to study ahead, you are welcome to do it. So you can actually work through the homeworks and quizzes earlier if you want to. And I have had students in the past that they said, yeah, I like this course so much that I'm gonna study this course on my own, and I will study in advance. And they actually started working out the problems from the material that was uploaded uh, in the canvas. Okay, any other question?
No, that was all. Thank you.
Okay. All right. So let me see. There was one more question. There are any rules on how many times you can submit homework or quiz? Yes. I would, as a policy, that the most recent quiz and homework will be graded. So that was Caden's question. Michelle has a question. Almost 6 hours? Yes. So, so that's why you get about 2 weeks to work on a quiz. And you get 1 week to work on the homework. Let me see. And you are welcome to explore the course. But here is something I want to tell you. If you go to the modules, okay, if you go to the module, just as a reference, I have uploaded the Spring 20 class recordings and PowerPoint presentations. And the reason I have done this is some students, unfortunately, are not in this country. They are out of United States. They could have some internet issues. So sometimes you may have access to internet, you may not have access to internet. So all this material is for the previous class is already up here. So you can study through the material at your own pace, depending upon your individual circumstances, and start working on the homework and quizzes. The information that you need to successfully complete the homework and quizzes is already posted in this module. So just because of the uncertainty associated with COVID, I wanted to put everything out there in case if you're not able to attend the lesson, if the timings are different, if there is an issue with the internet. So you are welcome to explore the course on your own. However, I just want to tell you that the problem that I may discuss in this class, they will be similar, but the actual values may be different, so that I won't be duplicating the information that is already posted. So I will work out some different problems. That way you will have additional help and a material from the last year's class as well as this year class that will prep you better. And if you want, you are welcome to review these PowerPoint slides or the watch video lectures before you come to class. That will help your understanding of the material. Now, the class recordings and PowerPoint slides for Spring 21 will be uploaded in this section. And I will try to do it immediately after the class, but sometimes converting it into 4K takes time. So within a day, the material should be on the canvas. If it is not, please remind me or send me an email and I will make sure that the material is posted. But in the meanwhile, please explore the course that will give you an understanding of the topics that we are going to study and the information that you will be getting throughout the course. Okay, before I begin actual discussion on the material, are there any questions related to the course content? Yes, the homework written on the binder paper is also fine, but what you need to do is you will have to scan that work, convert that into one single PDF and upload. Now, I will also want to tell you that some of these assignments are challenging. For an example, if you think about the design that we are doing here is sort of pen and paper design. So that those are like back of the envelope calculations. But when you go to industry, you will be using the software tools. So you will use ANSYS, or you would use SolidWorks, or you would use Abacus. So couple of assignments ask you to do something called as the finite element analysis. This is a super important skill. When you go to industry, you should be able to tell them not only you know CAD, but you know how to design the mechanical systems using CAD software. So that's why in some of these assignments, I have included finite element analysis. I have included some animation exercises, but I have actually included the videos where it is showing how to do that type of analysis step by step. So what you need to do is, what we need to do is when you try to do the analysis, you should go and watch the video and then perform the analysis the way it is shown. Jacob has a comment. I don't know what a green texture is. If you raise your hand, I can unmute you. Oh. Okay, looking at homework, I will check, but trust me that by the time the homework is due, that will be available for submission. Okay, any questions, comments? If you have any questions, use the chat window or raise your hand and I will unmute you. Homework 1 is the only one missing submit button. Okay, I will check after the class. Okay, so let's start. I'm gonna use a whiteboard for discussion. All these PowerPoint slides will be available after the class. So in EGR445 class, we are going to study design of mechanical systems. Now, I just want to clarify, you do not have final exam. I think I said that, but still I need to make sure you understand. No final exam. Quizzes are 60%, homework 40%. I would recommend having textbook. I have asked for the latest edition of the textbook, but if you can get access to an older edition or older version, that is totally fine as well, because I will be discussing the material in detail in this class. And no late homework quiz submission allowed. And we will use CAD software, SolidWorks or Autodesk Fusion are some possible options. SI version is of the textbook is totally fine. So in today's class, we will start with reviewing the information that you already know. So we will start with the basic concept of stress. So what is stress? Stress is defined as load divided by area. Now load is actually force. So this is nothing but force divided by area. The unit of stress is Newton per meter square. Now, what are the types of stresses? You can use the chat window to answer the question, or you can actually, if you want me to unmute, just raise your hand. Okay, pressure, compressive, any other answers? Tensile, shear, hoop. Okay, so let me give you basic types of stresses. There are two types of stresses. One is a normal stress, and the other one is the shear stress. Now, all the other stresses that you just mentioned in the chat window, for example, hoop stress, pressure, compressive, tensile, they are categorized under either normal stress or shear stress. So what do we mean by normal stress? Normal means perpendicular. If force is perpendicular to area, then the stress is normal stress. So there are two ways a force can be perpendicular to area. And believe me that all of you have studied this information in EGR 217, EGR 343, EGR 444, but many a times some simple fundamental concepts are difficult to understand. So I just want to make sure that we start with the basics. So if this is the load P and this is the cross-sectional area A, the stress which is given as sigma is given as P divided by A, where P is the force and A is the area, and that can be in meters square. If the stress is causing elongation, so elongation, that stress is tensile. If the stress is causing compression, that stress is compressive. Now, at this point, I just have to clarify the difference between compressive stress and pressure. Pressure is used, this is used in terms of fluids mainly, like liquids and gas. So pressure is the compressive stress in fluids. Now, if you look at the shear, the force is parallel to area. Now, what do I mean by force parallel to area? If you think about, again, the same rod, but rather than applying the force along the axis, if I apply force parallel to area, so this is the area, and this is the load P, the shear stress is given as tau, and that is given as P divided by A, but the force, the direction of the force is parallel to area. In the case of tension and compression, the force is perpendicular to area. Now, the next natural question is, so when we talk about normal stresses and shear stresses, what happens when these two types of stresses act together? Now, here is something I want you to understand. And in EGR 343, you might have studied the concept of principal stress and maximum shear stress. Now, these two stresses come in the picture when normal and shear stresses are acting simultaneously. So think about it, loosely speaking, that when you have normal stress, it is perpendicular to the area. If you have the shear stress, that is parallel to area, and these two stresses give rise to some resultant stress, and that resultant stress is termed as the principal stress and maximum shear stress. And we'll spend some time on this to make the concepts absolutely clear. So if you think about the bending stresses, so the bending stresses, they give you normal stresses. So the stresses that you study in bending, they are normal stresses. The stresses that you study in torsion, they are shear stresses. Sometimes you get complementary shear stresses, which means the shear stresses that are generated because of bending. And I will repeat this. You can get complementary shear stress. Now, please note, complementary means it's something that you did not ask, but you got. So you got shear stress because of bending. So basically due to bending. And if you look at the equation, it's VQ by IT. And we will talk about these types of stresses as well. Now, whenever you apply stresses, there is some type of deformation. So let's study the deformation caused by these different stresses. So let's discuss normal stresses. So when you have a normal stress, you could have elongation or compression. And probably you studied this in EGR444 and 347, that you have a rod and you are applying external load P. And what happens is this rod starts elongating. So the length increases, area decreases. So this is the final length, LF, and this is the initial length, Li. And delta L, or also called as delta L, is change in the length which is final length minus initial length. Strain is given as epsilon, that is change in the length divided by initial length. And strain is a dimensionless quantity. Now, you must have studied the stress strain curve for mild steel. And let me quickly show you what it is. So what I'm going to do is I'm going to apply the load and measure the deformation. So what I will have is I will have a load array and I will have a delta L array. So I will have load and I will have deformation. What I'm going to do is I'm going to divide load by the initial area. This is super important. A naught. So I'm going to call this A naught. A naught is the initial area. And I'm going to divide delta L by the initial length, the length of unstretched specimen. So what I have here is I have stress and I have strain. And what I'm going to do is I'm going to start measuring the loads and deformations, P1, P2, find out the values of stresses. So I will say I will find out sigma 1, sigma 2, I will find epsilon 1, epsilon 2, and then I kind of start plotting these points. So if this is epsilon 1, this is going to be sigma 1, then same thing at epsilon 2, sigma 2, and then I start plotting these points, and I observe that these points, they show an interesting pattern. This is for the mild steel. So initially, the area is, yes, the area that I'm referring to is the initial cross-section area. Because please understand that as you apply the load, that cross-sectional area decreases. So I'm not looking at the instantaneous area, but I'm looking at the initial cross-sectional area. So what happens is, initially, the stress is proportional to strain. So stress in this region, stress is proportional to strain. And this region ends at the proportionality limit. After this, what you have is the curve, the straight line starts curving. And what you have is, you have an upper yield point, you have a lower yield point, and then you have some sort of curve that actually goes up and then comes down. So what happens here is, and this is very interesting to observe, this region, what I'm showing here, is the elastic region, which means any time in this region, if you remove the load, the material or the specimen will go back to its initial length. So this is, if you think about it, and I want you to visualize this, this is like a spring. So in this case, the stress is proportional to strain, and the constant of proportionality is called as the Young's modulus E. So stress divided by strain is the Young's modulus. So stress divided by epsilon is Young's modulus in elastic region. Now what happens once you cross the elastic limit? Once you cross the elastic limit, the material gets deformed plastically or permanently. What it means is, I want you to visualize, if you go all the way over here, this is like you started with a spring, but you stretched it so much that it does not go back to its initial dimension. It remains a little bit stretched. What it means is, if you let the load go to 0, the material will follow this path and it will have a non-zero strain at 0 stress. So I will repeat this. Once you stretch the material beyond the elastic limit, the material starts to yield. To yield means to give up. Material sort of gives up. And at that point, if you remove the external load, the material will follow a path which is parallel to the straight line in the proportionality limit, but it will cross at a non-zero strain location. And that means that the material is permanently deformed. Now, what starts happening is, if you start applying the load, then even though the load it starts sort of dropping down, material gives up, and then even though the load is remaining same, the material starts stretching, and after some time you get grain boundaries crushing. So think about it like you start doing some work, you are putting some energy, and the grains, they start sort of getting compacted, and the boundaries, they crush against each other, and then the material starts offering resistance, and then that is when it goes up this hill. And then this is the maximum stress that the material can withstand. This is the sigma max that the material can withstand. But please note, the material is that plastically deformed. Now at this point, you are going to observe that for a ductile material, there is going to be the area will be reduced. So this reduction in area means instantaneous increase in the stress. And the instantaneous increase in stress at that reduced cross-section area exceeds the failure stress, which means it exceeds the strength of the material. The strength of the material is the maximum stress the material can withstand. So I need to write this down. So strength is the maximum stress material can withstand. So what happens is you exceed the strength of the material, and that causes the failure of the material. So you will see for a ductile material, you have cup and cone type of failure, and then the material separates. So elasticity has a life cycle to when it starts to lose its elasticity. We test this in tensile testing. Okay. This question is actually a fundamental question. I don't think I will be able to answer this question completely because of the time, but I'll tell you what it means. So elasticity is the property of the material, and there is an entire branch of stress that is called as the stress analysis that deals with elasticity. And when you are talking about the elasticity, we have to take into account not only the macroscopic events, like if I were to say the average stress distribution, but we have to look at the microscopic or the small region effects related to the stress. So if you think about the macroscopic effect, and this is something that you probably studied in 343, and so if you let the material unload in the elastic region, it will go back to its initial position. This is true in general sense, but there is the effect known as ratcheting. And that is called as stress ratcheting. So what happens is, even though you are cycling, a teeny tiny effect which may not be significant gets accumulated at the material level, and over a period of time that gets accumulated and the material behaves differently. Now, one way to analyze this is using the fatigue analysis, and probably you have studied variable loads. So variable loads, then Goodman criteria, Soderbergh criteria. And then something called as Gerber's parabola. So these are typically used in high cycle fatigue. There is also a branch of engineering which is called as low cycle fatigue. And those failures, the ratcheting failures, are very common in low cycle fatigue. ANSYS, SolidWorks can analyze for variable loads. They can do it, they can analyze for fatigue loads. But I have to tell you one interesting observation. For fatigue calculations in closed form can be done for simple geometries. For an example, if you have a rod, or if you have a cylinder, or if you have a prism, maybe you can do fatigue analysis using closed form. That also is actually difficult. So if you are dealing with fatigue load, variable loads, there are empirical relations, experimental observations that guide us during the design. For an example, if you look at the internal combustion engine, and we are going to study this in detail. In internal combustion engine, what happens is you have a cylinder, you have a piston, and you have a connecting rod. And then after the combustion, the gases exert the force on the piston. And believe it or not, the internal combustion engine, if you look at a simple weed whacker engine, okay, so for an example, lawn mower engine, or chainsaw engine, or a lawn blower engine, those run at 6,000 RPM. So 6,000 RPM when the engine is running, which means it's performing 100 revolutions per second. So it's doing 100 revolutions per second. And if it's a two-stroke engine, it's actually performing suction, compression, expansion, exhaust, all these strokes in one revolution of the crankshaft. If it is four-stroke engine, then suction compression takes one revolution of the crankshaft. Expansion, exhaust take one revolution of the crankshaft. So think about it, that you are actually doing 100 cycles per second. And I'm sure that you have seen these cycles in PV diagram. So suction, compression, expansion, exhaust. So you must have seen this thermodynamic cycles. So this all thermodynamic cycle, including ignition, generation of high pressure gases, expansion of those high pressure gases, these are acting at very, very high speed. And the load on piston, load on connecting rod, load on the crankshaft, they are all variable loads. And those are basically high cycle fatigue loads. So when we design, we will use concepts from high cycle fatigue to design piston or connecting rod or crankshaft. But a small answer to this question is yes, you can use ANSYS, SolidWorks, or Fusion to solve these problems approximately. Okay, at this point, 7:15, I'm gonna stop here. I'm gonna pause the recording, and then I will be back at about 7:30, and then we will continue the discussion. Okay, welcome back. Now what I want to do is I want to continue the discussion and extend the similar concept to shear stress. So when you have shear stress, you also have the deformation, but the deformation is not along the length. So for an example, if you have a block, and now we are going to apply the load that is parallel to the cross-section area, what happens is the block actually sort of deforms like this. So in other words, initially the element was rectangular with 90 degrees. It is no longer rectangular. The angle change. So the change in the angle. So initially it was 90 degrees and then it became gamma. So I'm gonna call this maybe theta. So the shear strain is nothing but theta radians. Now, similar to Young's modulus, there is shear modulus. That is also called as modulus of rigidity. And it is also similar to load the shear stress divided by shear strain. Yeah, these slides will also be uploaded. Now, something important about the shear stress is shear stress does not cause change in the length, but it changes the shape of the element. And that's something that you have to keep in mind. Typically, when you are trying to solve the torsion problems, you have shear stress. And I just want to spend a minute to give you some physical intuition of what is going to happen when you have torque. So if there is torsion, think about it. Initially, you had a rectangular element, and I'm going to show you this rectangular element over here. You had this rectangular element. Now, torque is nothing but force multiplied by the radius. So what happened that this force got applied, and that caused this element to deform. And what happens is this deformation continues along the length. So that's why we have the fundamental equation of torsion, wherein the angle of twist, shear modulus, and the torque relationship is expressed. And we'll talk about it in just a minute. But I want you to understand, whenever you have shear stress, usually you have a shear deformation. Now, there is something very interesting about the shear stress. and I want you to visualize this block that I have shown over here, and there is a shear stress acting like this. Now please understand, these two shear forces, they are going to give you, whether you like it or not, they are going to give you a moment. Okay, they are going to give you a moment. So however, the material develops internal shear stresses that resist this movement. So you have the reactionary shear stresses in this direction, and that keeps that material, that prevents material from rotating. So whenever you have shear stress, the shear stress cannot exist in isolation. Whenever you have a shear stress situation, the way we have shown over here, you are going to have a resistive or a reactionary shear stresses that prevent that material from rotating. Shear stresses are commonly observed whenever we are trying to solve the torsion problems, and the normal stresses are observed when we solve the bending problems. Now what I want to do is, I just want to give you a sort of a feel for these types of problems. So think about that we have a rod, and when we use the word rod, that typically means that that element is used for transmission of forces. So remember, when we use typically the word rod, we are transmitting forces. When we use the word shaft, we are transmitting torques. Now, this rod has three axes. This is the z-axis. Then you have y-axis, and you have x-axis. Now what I want you to visualize is, visualize the load parallel to y-axis or parallel to x-axis. So load parallel to y-axis or load parallel to x-axis. These loads will cause bending. So what will happen is, the rod would bend in this direction, or the rod would bend in maybe this direction. Now imagine you apply a torque. Torque is going to be about z-axis, and that is going to cause twisting. So you are going to have bending because of the forces along x and y direction, and you are going to have twisting because of the force that is about the z-axis. So that is the fundamental difference between the bending and twisting. In certain cases, what you could have is, and we will solve the problems like these, is consider that you have a shaft, and this shaft is supported at the bearings. And then on this shaft, you have a pulley. And so what you have is, the pulley has certain load. So the weight of the pulley, and then you have the torque. So now I want you to visualize. So you have the bending moment. So you have the bending moment M and the twisting moment T. So bending moment M and twisting moment, which is nothing but torque, or torque. simultaneously acting on this shaft. And these two together give rise to principal stresses. And obviously maximum shear stress. Now, I want to give you the equations, and I'm pretty sure that you studied, possibly derived these equations. And the equations for bending. So this is called as the bending fundamental equation. Is given as m divided by I is equal to F divided by Y is equal to E divided by R. And I want you to compare this with the fundamental equation for torsion. So fundamental equation for torsion is T divided by IP is equal to Fs divided by R is equal to G theta divided by L. And M is nothing but bending moment. I is moment of inertia. And this is also called as the second moment of area. Then F is the normal stress. Y is the distance from neutral axis. So neutral axis is the axis when the fibers are neither stretched nor compressed. E is the Young's modulus. And R is the radius of curvature. Now compare this equation with the fundamental equation of torsion, where T is equal to torque or twisting moment. IP is the polar moment of inertia, which is the moment of inertia about Z axis. And by definition, IP is equal to IXX, which is the moment of inertia about X axis, plus IYY, which is the moment of inertia about Y axis. You need to add those that give you the polar moment of inertia. Fs is the shear stress. R is the radius. Please note, when R is equal to 0, that is actually the axis, and there is no stress on the axis. G is the shear modulus or modulus of rigidity. Theta is angle of twist. And please note, this is in radians, and L is nothing but length of the shaft. Now, when we are going to solve problems, we would use these equations, the equation for bending, equation for torsion. We will use moment equations for moment of inertias. We will find out the moment of inertias of circular cross section. moment of inertia of rectangular cross section. And when we work out the problems, in few problems, I will show you how to actually calculate. Many a times, if we are using a standard cross section, then what we do is get the values of I and IP from something known as the design data book. So design data book or machinery's handbook. So we use these resources when we actually work out the design problems. Now what I want to do is I want to work out few simple problems, and the reason for working out these problems is once you start doing the homework problem, some of these problems are similar to the homework problem that I have asked you to solve. So I'm going to work out the problems on normal stress, shear stress, relationship between stress, strain, some problems on bending, and some problems on the fundamental torsion. But one thing, let me just clarify, and you know this, but I need to write this down for my own satisfaction, that for an isentropic material, consider a material which is homogeneous, continuous, and uniform. Initial length is Li. What happens is final length is Lf. Final length is Lf. And what happens is the length increases, cross-section area decreases. So the initial diameter, let's consider this as a circular cross-section, is Di. So, and then the final diameter is Df. So Df, Lf. So the dimensions that are drawn in black are initial dimensions, and the dimensions shown in red are the final dimensions. So Di is the initial diameter, Df final diameter, Li is initial length, Lf is the final length. So what I want to do is I want to find out the strain in the x direction. So I'm going to call this x direction. This is called as longitudinal direction. And then this is the lateral direction or y direction. So this is lateral. So what I'm going to do is I'm going to find out the strain in the longitudinal direction is L final minus L initial divided by L initial. This is the strain in the longitudinal direction. Now, the external force that is acting on this specimen is P. So P is the load. And I can find out the area of cross section as pi by 4 di square. That means I can find out the value of stress as P divided by A. The Young's modulus is given as stress divided by strain. Now I'm going to define change in the length as delta. So change in the length is delta. Now I'm going to substitute in this equation sigma divided by delta divided by Li. This equation can be simplified as delta E, sigma is P divided by A, delta divided by Li, and I'm going to take delta on the left hand side, and this equation now becomes PLI divided by AE. This is an equation that we may use, but this equation is very simple to remember. Think about it, is P divided by A is nothing but stress. And what I did is delta divided by Li is the strain, but I substituted the value of strain and took the delta on the left hand side of the equation. Now I can do the similar stuff in the lateral direction, but please note there is no force in the lateral direction. So I can say strain in the lateral direction is change in the length. Now here we have to be careful. So again, df minus di divided by di. But please note, df is less than di. On the other hand, lf is greater than li, which means the longitudinal strain in this particular example is positive, but the lateral strain in this particular example is negative. Now this case usually happens if you have loading only in one direction. So for an example, if you see if you were to apply the compressive load in the longitudinal direction, the longitudinal strain will be negative, but lateral strain will be positive. So there is an important parameter that most of you have studied, something called as Poisson's ratio. Poisson's ratio is the ratio with a negative sign of lateral strain divided by longitudinal strain. And typically for the materials like steel, the Poisson's ratio is expressed as mu. It's anywhere between 0.2 to 0.3. So please note that for analysis, strength of material and design analysis for isentropic material, two fundamental properties are needed, that are E, which is Young's modulus, and mu, this is Poisson's ratio. The shear modulus, which is G, can be found out from the Young's modulus and Poisson's ratio. So if you know the value of Young's modulus, if you know the value of Poisson's ratio, then you can find out the value of shear modulus. Now, some of you may have some experience with finite element analysis. So whenever you solve using SolidWorks or ANSYS or any finite element software, you have to enter the value of E and value of mu. Or in SolidWorks, you have to go to the material database and select the appropriate material so that the appropriate value of Young's modulus E and the Poisson's ratio mu is selected. So the problems that we are going to work out will use some of these equations. Before I start working out the problem, I just want to make sure that everyone understood the equations and keep these equations handy, and then we will work out the problems. Any questions before we begin? If you have any questions, you can raise your hand. I will unmute you, or you can use the chat window. So let me work out problem number 1. So consider a link that is shown over here. This is something similar to a sort of a dog bone link. And I'm going to show you the rotated cross section of this link. So if you look at this link, this is link like this. And if you look at the cross-sectional area of this link, this is the rectangular cross-section area. And what I have shown here is the rotated cross-section area of this link. So this link has the load as shown. So this is sort of a chain link, and there is an external load P. This load P is equal to 45 kilonewtons. This length is 45 millimeter, and this thickness, please note this is a rotated cross section. So what I'm showing you is this thickness. This thickness is 20. And this radius, actually the diameter, so the diameter of this circle is 75 millimeter, and the diameter of the internal hole is 40 millimeters. Now what we have to do is we have to find out the stresses at 2 locations. So we have to find out the stress at section AA, and we have to find out the stress at section BB. So find sigma AA and find sigma BB. So this is a simple case of determination of stress. The equation that we are going to use is sigma is equal to P divided by A. Now I want you to understand that the load is like this. In other words, if you were to visualize the cross-section area, and I want you to take a moment and visualize the areas, these areas, they are perpendicular to the line of action of force. So if I were to take sigma AA, the load is 45 kilonewton. So I'm going to write this in 45 10 to the power 3 Newton divided by the width multiplied by thickness, which is 45 multiplied by 20. And when I do this, I have the value of 50 Newton per millimeter square. And I would encourage you to use calculators and see if my answers are correct. Now, the interesting question is, what is the stress at BB? Now, to find the stress at BB, I need to find out the cross-sectional area, or the area that is resisting. But just for a second, I want you to visualize how this area is going to look. This area is actually something like this. So you have this area, and look at the dimensions that are given. This is 75. This is 40. And this thickness is 20. So sigma BB is going to be 45 10 to the power 3 divided by cross-sectional area, which is 75 minus 40 multiplied by 20, and that gives me the answer 64.3 Newton per millimeter square. So in this case, the areas are different. Any question? Everyone understood this problem? Okay. Let me work out the second problem. So in this problem, it's a hydraulic press. That exerts 3.5 meganewton. So 3.5 10 to the power 6 Newton. This hydraulic stress applies 3.5 meganewton. The load is carried by two steel rods. Now, if the safe stress, so sigma safe, is 85 megapascals, and the Young's modulus for the steel is 210 kilonewton per millimeter square. First, find diameter of rods and then find extension of the rods. So I want you to think about this problem. So what you have is you have a hydraulic press. So think about it like I'm going to show a hydraulic press. And this is the hydraulic press. And what happens is there are actually two rods that are taking the loads, the identical rods, they are taking the load of this hydraulic press. So think about it like this piston is coming down. So this is the piston. And this is exerting 3.5 meganewton. actually I made a mistake here. Basically, the rods, it should not be extension, it should be compression. So this is one rod, this is rod number 2, and note that this load is passing through the center line. So this is a design problem, and we need to find out the value of the diameter and the extension. The length of the rod is given as 2.5 meters. So length of the rod is given as 2.5 meters. So how do we solve this problem? Please note the total load is shared by 2 rods. But before we discuss that, I just want to spend a minute on what is this sigma safe. Now sigma safe is also called as sigma design, which is nothing but sigma yield divided by factor of safety. Now I want you to quickly remember the stress strain curve that we talked about. You have sigma, you have epsilon. Now, whenever we design an engineering system, we do not want to exceed the yield stress. And why do we want yield stress to be our limit? Because you don't want to sit in a car which kind of permanently deforms. Mind you, it deforms, but it does not fail. So imagine you sit in the car and the car's chassis deflects so much that you're no longer comfortable. So you don't want to exceed the threshold of yield stress. So this is sigma yield. So that is the design limit. So maximum you can let the material go up to the yield stress. However, here is what's going to happen. The material is going to have its own impurities. There will be some workmanship error. There could be some grain error. There could be some blowholes. So you can't ensure that that material will be perfect. So what you want to do is you want your design stress to be much, much lower than the yield stress. So your safe stress or design stress, so sigma safe or sigma design, is much, much less than sigma yield. And the ratio between the yield stress and the design stress is called as factor of safety. So for an example, for the sake of discussion, if your yield stress is say 300 Newton per millimeter square, if your yield stress is 300 Newton per millimeter square, and you say, I want my design factor of safety to be 3, which means your sigma safe or sigma design is going to be 100 Newton per millimeter square. Sometimes when you look at the design data book, you have a choice to select particular factor of safety. And depending upon the application, for example, humans are involved or it's the application is mission critical, then you want to make sure that you have enough factor of safety so that that component or that design does not fail. But you have to have a balance, because if you increase the factor of safety, then what's going to happen is the dimensions are going to become larger. So for example, if you have an aircraft, you cannot use a very high factor of safety because the weight of the aircraft increases, and that causes more fuel consumption and other problems. So you have to balance these two things. So if they give you the yield stress and give you factor of safety. Then you can find out the design stress. But in this particular problem, the design stress is already given to us. Our sigma safe is 85 megapascals. And to clarify, mega is 10 to the power 6. So 85, 10 to the power 6 pascals is Newton per meter square. Now, if you look at the dimensions, all the dimensions are in millimeter. So what I'm going to do is, I'm going to convert this into Newton per millimeter square. So 85, 10 to the power 6 divided by 1000 millimeter square. That gives me safe stress as 85 Newton per millimeter square. Now this safe stress is load divided by area. However, please note that there are two rods. So rod 1 and rod 2. So there are two rods. So what I'm going to do is, I will have 3.5 10 to the power 6 Newton divided by 2, because there are two rods, multiplied by pi by 4 d square. And when I solve this, I can find out the value of d, and my answer is 162 millimeters. And please note why there are two rods, because clearly this hydraulic press, you don't want it to go out of alignment. So it needs to go up and down in a straight fashion. That's why we have symmetric supports. So the diameter is 162. Now, how do we find out the compression? For that, remember the equation delta is equal to PLI divided by AE, where P is the load. That load is 3.5 multiplied by 10 to the power 6 divided by area is what we have is 2 times pi by 4 times 162 square. What this gives me? This gives me stress in each rod. And that is super important, because to find out the deformation of each rod, I need to use the equation E is equal to stress divided by strain. This is for single rod. So I'm finding the stress in each rod multiplied by the initial length of each rod, which is 2.5 meters. I'm converting 2.5 meters into millimeters, divided by Young's modulus. And a word of caution, please note, Young's modulus is given in kilonewton per millimeter square. So what we need to do is, we need to change this 210 multiplied by 10 to the power 3 kilonewton per millimeter square. And when you solve this equation, you are going to get the value of delta, and the answer that I got is 1.01 millimeter. So the compression in each rod is 1.1 millimeter. The diameter of each rod is 162 millimeters. Okay, before I proceed any further, are there any questions? So let's work out the next problem. Everyone understood these two problems? Okay, let me work out the next problem. So here we have sort of a knuckle joint, and I'm going to show you how that joint looks like. So I'm going to call this sort of a knuckle joint. So it has a left half and the right half. And what you have is you have a pin. This pin is going through the center. So I want you to visualize that you have a pin and then here is this joint and there is an external load. Now I want you to sort of visualize how this system looks like. I'm gonna try to draw a sort of a three-dimensional view. So what you have is you have something like this now, and you have a pin that kind of goes through this. So there is a pin here, and now what you have is you have another end over here. Now you have the left hand side, you have the right hand side, and what happens is these two ends, they fit, and then what you do is you insert the pin. Now what you have in this configuration is you have 80 kilonewton of load. So this joint, and this is similar to a knuckle joint. We will study the design of the knuckle joints in detail. So you have this 80 kilonewton of load that is transmitted. Now I want you for a minute to visualize that this is actually a pin joint, sort of, it's a pin joint. And there is a reason that we are applying a tensile load, because there is a possibility that if this joint is not properly constrained, the hinge or the pin, that the joint would rotate about the pin. So that's why we are applying the 80 kilonewton of tensile loading. Now, if the maximum permissible stress in the bar, now please note, this is the pin, this is the pin, and this is the bar. Again, this is the bar, and the bar cross section is circular, so it's a circular cross section. So this is a circular cross section. So in this joint, we have to find out, say we have to design this joint. So what we have to do is we have to find out diameter of rod and diameter of pin. And what I'm going to say is, just to make the problem interesting, these two are made up with different material. For an example, the rod, so, or the bar or rod, I'm going to call this rod 1 and I'm going to call this rod 2. Rod 1 and 2 are made up with, say, steel. So rod are made up with alloy steel with sigma safe is equal to 100 Newton per millimeter square. And the pin is made up with mild steel, and the pin is made up with mild steel. And sigma safe for pin, it's say 80 Newton per millimeter square. Now what I need to do is, with this information, I need to find out D rod and I need to find out D pin. Now first and foremost, I want to ask you this question. What will be the type of stress in the rod? And the options are, so I'm asking what is the type of stress in the rod? So what we are going to do is, I'm going to look at rod. My question is, what is the type of stress? And the options are tensile, compression, or shear. So what would be the type of stress in rod? Okay, I actually have given you the answer right here. Look at the force. Look at the area. The force is perpendicular to area, which means the stress is normal. Now, please note that this force is going to cause an extension. That means it is tensile. So you are going to have, in the rod, you are going to have sigma tensile. That will be P divided by A. Tensile stress is 180 kilonewton 10 to the power 3 divided by, it's a circular cross section, pi by 4 d square, and that gives me the diameter of the rod. So diameter of the rod, my answer is 32 millimeters. Now let's think about the stress in the pin. Now I want to show you the force on the pin. Tell me what type of stress would be in pin. The answers are, potential answers are tensile, compression, and shear. Think about the way this pin will be sliced off. This pin will be sliced at two ends. So it will be sliced over here and it will be sliced over here. So basically, if you look at this pin, that pin will be sheared off something like this. So the pin will be in double shear. So the stress in pin, and I'm going to show it over here. pin is tau, because it's a shear stress. It will be P multiplied by 2 times area of pin. And why the area of pin will be 2 times? Because see, the pin is in double shear. Now, what I'm going to do is, I'm going to substitute AT is equal to 80 10 to the power 3 divided by 2 multiplied by pi by 4 diameter of pin square. And when you solve this problem, you are going to get the diameter of the pin. And my answer for the diameter of the pin is 26 millimeters. So everyone understood that in this problem, what we have is, we have shear stress and tensile stress. Any questions? If you have any questions, please type in the chat box or raise your hand and I would be happy to answer. So moving on to the next problem. Now this is an interesting problem. Find the force needed to punch a circular blank of 60 millimeter diameter and 5 millimeter thickness. Now, so what does this mean? So think about that you are using a punch to punch a hole. So usually you have the flat sheet of material. This material will have some thickness and you're going to have a press tool. So for an example, a punch. And what will happen is this punch will go down, hit this raw material and basically drop the blank. So this is the circular blank. Now, what I want to do is, I want to ask you this question. If the diameter of the blank is 60 millimeter, thickness of the blank is 5 millimeter, we have to find out the total force that is exerted by the punch. What type of failure is on the blank? So whether the failure on the blank is in tension, shear, or compression. Now, this problem has two parts. So what I want you to think about is the force is being applied by the punch. So punch is applying the force, but the blank is actually sheared circumferentially. So this is nothing but case of circumferential shear. However, the stress in the punch, so please note there is this punch. Stress in the punch is normal. So circumferential shear in blank and normal stress stress in punch. So if you look at the failure of the blank, the stress is equal to P divided by A. And this area is nothing but the circumferential area. And since this is a steel, so the shear stress, ultimate shear stress, tau ultimate is equal to 350 Newton per millimeter square. Now, a word of caution. Here, we want the failure to happen. So which means we need to go all the way to the strength of the material so that the material fails. That's why we are using the ultimate stress, not the yield stress. So ultimate stress is 350. We have to find out the value of P, and the area is pi times D multiplied by T. So P pi times 60 multiplied by 5. And this will give you the total force. And my answer for total force is about 330 kilonewton. Now, an extension to this problem is the stress in the punch. So what is the stress in punch? Now, please note, stress in punch is going to be compressive, sigma C, and that would be P divided by A. And please note, the diameter of the punch has to be same as diameter of the blank. Only then you are gonna get an accurate blank. So P is going to be 330. So 330 kilonewtons divided by area is pi by 4 multiplied by the diameter square, 60 square, and the answer will be in Newton per millimeter square. But please note, this is compressive stress. And you have shear stress in the blank. Everyone understood about normal stress, shear stress? Any questions on this problem? So the question is, we have to find out the force that is needed to punch through the blank sheet. Yes, the minimum force. But what I did, I kind of did an extension, and I said that, hey, we are punching the hole through the blank or the material. So as we do that, what would be the compressive stress on the punch? So that is the problem. Any questions? Michelle, did I answer your question? Okay, good. So next stress that I would like to discuss is the concept of bearing stress. Now, what do I mean by bearing stress? Think about a shaft or a rod that is supported in a bearing. So for an example, what you have is, and I'm going to try to show you how this looks like. So usually what you have is, you have some sort of a bearing, And then you could have a rod or you could have a shaft. And I'm going to show you that this is the bearing. This is the bearing. And what happens is you have this shaft. Now I want you for a minute to focus on the interface of the shaft that is resting on the bearing surface. So what I want you to do is, I want you for a minute to visualize the distribution of the pressure on the bearing. And the distribution of the pressure on the bearing usually takes the shape as I shown over here. So this is the variation of bearing pressure. And what does this bearing pressure cause? So whenever, if you see shaft that are located in the bearing, you might see some sort of pitting or maybe some sort of material removal. And that is because of this stress distribution. And this is called as the bearing stress, sigma B, which is called as the bearing stress. And the approximate equation for the bearing stress is load divided by the projected area. Now that is correct. It's sort of a compressive stress. So let me tell you what is happening. So if you look at the way the whole thing is, the load is sort of initially distributed like this. However, please note that what you have is an ideal situation. Usually, the load is not uniformly distributed. So this is an ideal case. But in actual case, the load is not distributed uniformly, and you will see the load is distributed something like this. That means the pressure is not uniform. So what we do is we use an approximate equation, and this approximate equation is the load, which is the load that is on the shaft. So this is the load P divided by the projected area. So this, if this is the load P, the projected area is nothing but, if this distance is L, if this diameter is D, the projected area is nothing but P divided by D times L. And this is a conservative estimate on the pressure. And at this point, you may ask this question: hey, since it's a semicircle, why don't we look at the semicircular area? And that's totally fine. But in the ideal case, the load is uniformly distributed. But in actual case, the load is not distributed uniformly. So to account for the non-uniform distribution of the load, we consider the projected area. So if you have a bearing surface, sigma B is given as load divided by the projected area. Okay. And this will be super important when we try to work out the problems. When we are trying to design the systems that are subjected to bearing stresses, or when we are going to design the sliding contact bearings, at that time, this will be super important. Now, for the completion purposes, let me give you something called as the thermal stress. Thermal stress is given by Young's modulus multiplied by thermal strain, epsilon T. So this is thermal strain, and this is Young's modulus. This is equal to sigma T. However, there is something I want to clarify. If you just have a rod here, the change in the length of the rod because of the change in the temperature delta T is given as, so delta L is equal to alpha delta T times L, where alpha is coefficient of thermal expansion, change in the temperature, and length. Now, if the rod is free to expand, then the stress is equal to 0, because rod is allowed to expand in, say, both directions. So there is going to be thermal strain because there is change in the length, but there is no thermal stress. On the other hand, consider that you have a rod and that is constrained and you are not letting it expand. So as you increase the temperature, the rod is going to try to expand, but the support is going to exert force, and that would cause stress. So when the rod is constrained, only then the thermal stresses that come in the picture. And for the sake of completion, I'm going to say epsilon T is given by alpha times delta T. And please keep this in mind, because many a times what we have to do is we have to take into account and compensate for the change in the temperature and the effect of change in the temperature, the dimensions change, the components elongate or compress or contract, and we have to make sure that even though that machine or that component is subjected to variation in the thermal stresses, it's able to sustain the loads and does not fail. Okay, I'm gonna stop here today, but we have 2 minutes. If there are any questions, I would be happy to answer.